Hello. In this movie I want to demonstrate how to generate the model setup for an ultrasonic thickness sensor. This is the first part where I want to handle the geometry generation and mesh generation using the preprocessor Trelis. So the model that we want to take a look on today is an ultrasonic thickness sensor that is depicted here on the right side, and the model consists of the medium that we want to know the thickness from, for example paper. This is depicted right here, and then we have an ultrasonic piezoelectric sender here on top that will launch an acoustic wave through an adaptation layer, and the air here in between the adaptation layer and the paper. Then the paper will start to vibrate, and an acoustic wave is launched on the other side as well, and that will be recorded by a receiving piezoelectric transducer. Okay, here are some dimensions that we want to use for the components as well as a small sketch. So we have the sender and receiver piezoelectric device, which should have a diameter of 10 millimeters, a thickness of 1 millimeter, and the angle that will be used is 27.21 degree. This is mainly to get some hands-on distance length, as you can see here on the lower side. We also want to use an adaptation layer with the same diameter, thickness 2 millimeter, and the minimum distance between the paper and the adaptation layer that is depicted right here should be 3 millimeters. The small part of the paper that we want to look on has a length of 50 millimeters, width of 20 millimeters, and a thickness of 100 micrometer. Okay, so the next step that we want to do is we're going to start Trelis. So this is the graphical user interface of Trelis. You can see on the top left side some icons for new projects, open save dialogs. Here we have something I'll come back to later, a journal editor. Here we can have a look on the different view settings, whether it should be shaded, transparent, with hidden lines or something like that. Here a switch whether we want to see the geometry or not, and here a switch whether we want to see the mesh or not. Here we can update the display, here we can zoom, here we can resize, and here we can see the dimension of our model easily. Let's start on the right hand side. So there are mainly 5 icons. We only take a look at the 3 of them. So on the left side there's the geometry icon that will allow us to generate geometric entities. Here the mesh command panel that allows us to set up the mesh for this model, and here later on we can define certain element groups or regions and groups for NACS later. So we're gonna start by generating the model. So maybe we start by setting up the paper at first. So the paper is mainly here called a brick. We're gonna do the model in millimeters, and as we can see the width of the paper should be 20 millimeters, then the length should be 50 millimeters, and finally the depth should be 100 micrometers. So we're gonna do that, and the first thing that we see is that very small brick. So the next thing I'm gonna do is I'm gonna create the cylinders for the piezoelectric devices. They should have a height of 1 millimeter and a diameter of 10 millimeter, or a radius of 5 millimeter. So here is one of them. If we're gonna view it in the volumes tree, then we have currently 2 volumes, and we're gonna generate another of those cylinders for the sender and the receiver piezoelectric disk. Now for the adaptation layer, we can leave it like that because the radius is the same, just the height is 2 millimeters. And also for those, we generate 2 cylinders. So 1, 2. And as you can see, Trelis generates the entities within the center of gravity of the origin of the coordinate system. So what I'm gonna do right now is I will move the piezoelectric disks and the adaptation layers away first and then rotate the whole disks so that we have that disks in a certain angle to the paper. Therefore, I'm using right here the transform volume action. Here we can select align, move, reflect, rotate, and scale. We at first use move. Our piezoelectric volumes have the volume IDs 2 and 3. So I'm going to move the volume 2 in. You can see it right here in Z direction with a certain distance. So the set distance should be, as we have computed previously, 8.5 millimeters. So this at first, and the second one we're going to move minus 8.5 millimeters. And the next thing is I'm going to do the same for the adaptation layers. They are moved 7 millimeters away from the center of gravity, or minus 7 millimeters. Okay, so this is not volume ID. So here we go. So the next step is I'm going to rotate those disk devices using the rotate command, and here I could now either write volume IDs 2, 3, 4, 5, or I just write 2, 2, 5. And I want to rotate around the x-axis, and the rotation angle was 27.21 degree. I can at first preview what will happen, and it looks like it is what I wanted to see. So this is finally the model that I wanted to obtain. Now there's another thing I want to generate, and this is the surrounding air, so the air between the paper and the transducers. Therefore, I generate another brick. Here the width and height I keep the same, but the total height of those bricks should be 12 millimeters, as we could see in the dimensions tab. And I generate 2 of those volumes. And so the next thing I'm going to do is I will shift those volumes so that they will be placed directly adjacent to the paper domain. Therefore, I can use this move action, and I want to move volume ID 6 in Z direction, and I have to move it. If we want to compute something, we have to use those rounded brackets. So we use half of the height of the piezoelectric of the air volume, so these are 6 millimeter plus 50 micrometers. This is so that it will be moved just on top of the paper, and volume 7 is going to be moved in the other direction. If we use those transparent views right now, we can see what happened. So this is mainly what we have set up. Now there's still one thing missing, and this means here on the back side of the piezoelectric discs there should be no air, of course, because there's typically a housing or something like that. So we have to create some cylinders that will be placed here adjacent to the backside of the piezoelectric discs, and later on we will just subtract all of those cylindric volumes from the paper cubes. So that means we again generate two cylinders with a height of, right now it doesn't matter, let's say 12 millimeters, same radius 2 times, and we will also move them right here. So this is volume 8 in Z direction, and we could see that we've been moving the piezoelectric disc 8.5 millimeters. Then we have to add another half a millimeters to get to the surface of that piezoelectric disc, and then we need again to add half of the height of that cylinder, and now we can preview. Okay, it will be here. So we use that once for volume 8 and this for volume 9. And then we will rotate both of those volumes, 8 and 9, with that angle. Press apply, and it looks like it is finally what we wanted to obtain. So now we have all the volumes that we wanted to have. Next step is that we will subtract the cylinders from the air volumes. This will be realized by using here this subtract Boolean operation. So the body that is subtracted from is that large cube here, so it's the body ID 8. We can just click here, and the body IDs that we want to subtract are body 2, 4, and 8. So 2, 4, and 8. And at first, let's keep the originals, otherwise those tool bodies would be deleted. I press apply once. A new volume with the ID 10 is generated, and I'm doing it a second time now with this air volume with that piezoelectric disc. So let's type it like that: 3, 5, and 9. Okay. Now we can take a look at those new volumes, so we can see that the cylinders have been cut off. That means we don't need volumes 6 and 7 anymore, so we can just delete them. Another thing that we don't need anymore is those two cylinders on top and bottom. We also delete those. So this is finally what is left from the whole model. So one thing that is missing in the end is that we will imprint and merge all our bodies in order to get a conform mesh in the end. So this is what we did right here. So now that the geometry has been generated, the next step is to set up the mesh. Therefore, we go here on the top right side to the command panel and go to the mesh mode, and here we can select mesh settings for volumes, for surfaces, for curves, for vertices, etc. We want to set up the mesh settings for the volume, and at first we want to specify the mesh size. At first, maybe for volumes 1 to 5, that is for the paper and all the piezoelectric discs and the adaptation layers. You can either specify here in automatic mode, whether you want to have a coarse or a fine grid. We want to specify something with an approximate size, and the approximate size of our mesh should be around 1 millimeter. We just specify that here for the paper and also for the piezoelectric discs. Press apply, and we can directly press mesh, and so we can see that a hex mesh has been generated for the piezoelectric discs and the paper as well. Then finally we have our two air volumes, volume numbers 10 and 11, and here we also want to specify a certain element size, and here we can use an analytic expression that will be put between those curly braces, and we want to compute that mesh size from the speed of sound, 343,000 millimeters per second is the speed of sound in air. We want to use a frequency of 50 kilohertz, so we divide that speed of sound with the frequency and arrive at the wavelength, and the wavelength should be discretized with 20 elements. So we apply that to our air volumes, and so the next step that we will carry out is we go here to the mesh settings of, again, volume 10 and 11, and here we specify default values that are normally already visible right in here. We apply that scheme to both of those volumes, and then again press mesh. Okay. So it takes a little time, and then we finally should arrive with the complete mesh. Okay. So just for performance reasons, we maybe deactivate the mesh view right here, and then we go to the next step, and this is right here on top, where we can define groups and materials. And here we can define NodeSets, a set of nodes, SideSets, this is a set of elements, and here blocks. And we start by defining some blocks that will later be used in our model for defining regions and groups. So here we define a new block. Those blocks will later on appear right here. It will have the block ID 1. We want to use volume with ID 1. We press apply, and here appears block with the ID 1. Then we use the block with the ID 2, and this will be assigned to the piezoelectric sender. Next block right here, volume 3, the receiver. Block 4 is going to be the adaptation layer on the sender side. Block 5 is going to be the adaptation layer on the receiver side. Finally, block 6 is going to be our two air volumes. So those blocks can also be renamed. Therefore, I go over to that side, press F2. This is the paper. This is around, let's call it sender piezoelectric. Let's call it receiver piezo. Let's call this one sender adaptation and receiver adaptation. Finally, last block with the name air. Okay, so now we've set up all our regions. Now some things are still missing, and this is, for example, we will need for the acoustic boundaries, we will need all three surfaces. So that means this surface, and this surface. So those surfaces will be used, and here we want to define one side set. Those side sets appear here. We can also directly put a name like this. It's called, for solving boundary condition, or let's call it air bound. Then we still need something. Here if we right click on volume 1, we can also isolate it. And we need the fluid structure interface of the paper, and this is simply the top and the lower side of that box. We again select the surface, click on the top side, on the lower side, press apply. We call this FSI, fluid structure interface. Then I want to select my piezoelectric sender. I also isolate it. I need 2 electrodes for applying the voltage. I call this side set 3, and side set 4 will be the lower side. So I could call this sender top L for top electrode, and sender bot L for bottom electrode. This FSI is not completely correct, because it should be maybe called FSI paper. Later on we will also need something for the fluid structure interfaces of the piezoelectric devices. So then I take the next piezoelectric device right here. Maybe we could also turn on the visibility of the paper, so it's easier to know where we are. So I call, sorry, like that, one side set, and then here another side set, and here also we're gonna call this receiver top L and receiver bot L. Okay. Is there anything else still missing? Yes. On the bounds of the paper, mainly here. Let's do the solid model. I want to specify another side set using this face and also this face, and we will use those 2 faces as absorbing boundary conditions. Let's call it paper bound. So there the paper should be infinitely long, so we will apply later on there a boundary condition that allows us that for the mechanical domain. So only one thing is still missing, and this is the fluid structure interface of those piezoelectric discs. And so here we could use, for example, those 3 for one time, and then maybe on the other side we are using, those 3 surfaces. So this is on the one hand fluid structure interface sender, maybe the other way around, sender fluid structure interface, and here also receiver fluid structure interface. Maybe we call this paper FSI. Okay, so these are all the blocks and the side sets that should be required in order to get our model. So the one thing still missing is how we can write a model for NACS, our simulation software. Maybe at first I'm gonna save the model, call it, for example, PaperThickness Trelis. Everything is saved. It's perfect. So currently there's nothing in here concerning our NACS interface. Therefore we go to Tools, Components, and here we can click on the Add push button. Then we navigate to the installation directory of our NACS installation. This is at C program files, SIMetris, NACS 2.3, shared Trelis, and there's something called NACS interface. This is what we select. Then a dialog box opens asking us for the component's class name, and this has to be NACS component. Then we finally click load. Here we can see that it is currently still unloaded, but at the bottom it says NACS interface has been loaded. If we close that dialog and open it again, we can see that it is really loaded. So since it's loaded, we can see now in the menu bar that there's a menu entry NACS, and here's a write NACS mesh file. I select that, and this is how our model currently looks like. We have here our regions corresponding to the blocks. We have our groups corresponding to the SideSets and the NodeSets. Here we can see how many nodes and elements there are in our model currently. We have a first order mesh. If we want to change it, we could here easily specify 2. It's a 3-dimensional model, and then we just select the mesh file where we want to store it. I call it 3D paper thickness 50 kilohertz, let's say today, so that we can see what happens. Here we can specify the scale factor. We require SI units, so we need meters, and we generated the model in millimeters. That means the scale factor is 1 to the times 10 to the power of -3, and so we press save. Now here in the command line we can easily see what's happening. The nodes are compressed. Now the nodes and the elements are compressed, and later on we can also see that region information is written. So this is not a super fast machine, therefore it takes some time. Now the groups have been written, and now you can see that the mesh file has been generated. So this is where we could start to set up the simulation, but this is going to be part of another webcast. One thing I still want to show you is we did a lot of things. Can we recall what we did? And therefore I open right here the journal editor. Here we can generate some script files, and what I'm going to do is go to File, Import, Command tab, and what we can see right here is all the commands that have been processed in the last few minutes. And so there's something called reset, and this is where our model has started. So reset is a scripting command, and then you can see these are all the operations that we carried out to obtain the model that we finally have right now, up to the point where we saved that Trelis file. Now we can of course also modify that script, and something very handy is of course to use scripting variables to generate the model. And therefore we have a command language called iprepro. You can easily look up the syntax in the manual of Trelis, but at first I will just set up all the parameters that we've been using. So maybe we start with a paper. If you want to define a parameter, you use that hash sign and then curly braces and then the parameter name. That time it's paper W, like the paper width. And that should be 20 millimeters. And if we want to use a scale model, maybe we define a scale factor so we can easily switch the dimensions. The scale factor in our case is 1000. Then we have the length of the paper, 50 millimeters times the scale factor. And we have the paper thickness, it's 100 micrometers times the scale factor. Then we have the piezo, let's say radius, it's 5 millimeters. We have the piezo thickness, it's 1 millimeter. We also have the adaptation layer thickness, it's 2 millimeters. And we have the minimum paper distance, it's supposed to be also 3 millimeters. And finally we have the angle of the piezoelectric device, and it's 27.21 degree. Is there something still missing? I don't think so. And, now we can easily exchange, for example, right here, the dimensions. Here we restricted 20, we could write the paper width. And if we want to use the variable names, we have to put them in curly braces at the position where the parameter will be placed. So like that. Down here we have piezo thickness and the piezo radius 2 times piezo thickness. Also here we have the adaptation layer thickness. Also here. So now those are the lengths. They can also be, of course, computed by, I will not provide something special to compute those. Then we have the piezo angle, and as you can see, there are some commands that have a preview in it, so those can easily delete it because we don't have any use for them. Okay, something still missing up here is the air, let's call it thickness, 12 millimeters times the scale factor, and then we can replace this with the air thickness. Maybe it's easier to copy it from the top 2 times, but now here we have the air thickness. Okay, there's an error up here, just one curly open braces, certain move commands, and here the, let's do it like that, radius is bigger, so radius, we also need that 2 times, again with the preview. Yeah, and you can see here, for example, no, it's not easy, we have to keep it like that. Okay, here we have the subtract operations, and right here our mesh, our geometry is ready, and now the mesh setup will be carried out. And then here the only thing that's still being done is the block setup. use certain names, and also here, maybe at first we generate all those side sets, and then in the end we just use the name because we changed the name several times. So let's see. SideSet2 has that name finally, so that's it. If you want to use comments, just use the hash sign in front of it. So for example here, reset the model, specify some parameters, create geometry, it's gonna be paper, pieces, adaptation layers, we start with the volume number 7 that did not exist. Move and rotate it, pieces and adaptation layers. This is what's gonna happen here. Create air volumes. Create cylinders to cut out air. Okay. Do Boolean operations. So this is what had to be carried out. Delete unused bodies. And merge alls for a conform mesh. Okay. And then here say start meshing. One thing that we could do is also specify the mesh sizes. For example, here E size paper would be 1 millimeter times the scale factor. A size piezo also 1 millimeter. So this is of course just for demonstration purposes. E size air, let's do it that way. Speed of sound in air is 343 meters per second. Maximum frequency should be 50 kilohertz. And her lambda should be 20. So E size air is C air divided by F max divided by ln per lambda times scale factor. So now we have to do a little different. Volume 1 size, E size paper. Here we have E size piezo, and finally here we have E size air. I think it was right, E size air. So once we are finished, we can save that script as well. Because like that, and then we just press play and we'll see whether it works the way that we supposed it to work. Everything is generated. That was pretty fast. Something went wrong concerning the air mesh size, element size. Let's see what happened. Yeah, the element size in the air is far too high. Has to be a typo in the setup. Yeah, here. It's not 50 kilohertz, it's 50 millihertz. This is, of course, not reasonable, therefore we start it again. Now the meshing should take a little more time, looks like that. Yeah, that looks better. Okay. So this is finally how you can easily write a script that allows you to reproduce what you did. I think this is everything that I wanted to show concerning using Trelis as geometry editing tool, or geometry generation tool, and also for carrying out the mesh setup in Trelis. So thanks for watching and goodbye.